Welcome to our AI seminar series. Today, it's my pleasure to introduce Mohammad Rostami, which I'm sure all of you know. He's a research assistant professor in the USC Department of Computer Science and a research scientist at ISI. He received his PhD degree from the University of Pennsylvania in 2019, and his research right now focuses on machine learning in data scarce regimes, including domain adaptation and low shot learning, improving efficiency of learning, including continual learning and collective learning. And today he's going to talk to us about autonomous learning through prototypical distributions.
Okay, thanks, Deborah. Let me share my slides. Okay, so please feel free to ask questions through the chat box, and Deborah is gonna stop me to answer potential questions. So the title of my talk is Autonomous Learning Through Prototypical Distributions, and this is a topic that I've been focused recently. I'm gonna give a background and some motivation, and then focus on two applications in domain adaptation and presentation attack detection that benefit from this idea of using prototypical distribution. So I'm sure many of you are familiar with standard machine learning framework. The way that we model machine learning in probabilistic language, we consider in particular a classification problem. We consider that we have a joint distribution, in this case, for an easy example of binary classification, where we have images of cats and dogs. And our goal is to train a function which is parameterized by this parameter theta, such that given the input, we can recover the corresponding label. Now, an easy example, we can model this as a linear model, and our goal is to find the parameter theta such that we can give the least expected error on predicting the label for any given sample drawn from this distribution. However, solving this expected a true expectation minimization is not tenable, and what we do in practice is to collect a training data for which we know the labels, and rather minimizing the true risk, we minimize the empirical risk given a suitable loss function to match the input data with the corresponding labels. Now, naturally, since we've replaced the original optimization with this surrogate optimization, one might ask, when does a model generalize well? And this is a question that has been explored in theoretical machine learning, in particular in pack learning paradigm. It has its own field, but what I want to provide an answer to this question is somewhat heuristic, and more specifically within deep learning. When we train a deep network to solve a classification problem, usually we have several layers, and my answer to this question, when a model is going to generalize well, is that given an input distribution, the distribution that we talked about in the previous slides, a deep net is going to generalize well or come up with good predictions if we can transform this input distribution into a multimodal distribution in the embedding space, meaning that in this classic example from MNIST dataset, we can map the data points into this embedding space such that data points that belong to the same class form a cluster, and these clusters are separable. In this situation, if we form an internal distribution like this, which is multimodal, and the modes are separable, and the data points for each class are mapped to one mode, then we can simply train a classifier, because as you can see in this image, which by the way is created by real data, the classes are separable, and so geometric distance kind of represents meanings in the internal distribution. Now, the problem is generally when we train a model, our expectation is during testing time or model execution, we see the same distribution. However, this is not true in practice because usually we have this phenomenon called domain shift, which means that in the input distribution, we may see some drifts as time passes by, or when we train a model on a domain and test it on a domain that is a little different. For example, consider that we've trained a model on the MNIST dataset, just 10 digit classification task, and we want to test it on the SVHN dataset. It's a similar dataset. Again, we have 10 classes, digits, yet the input is a little different from MNIST. In that situation, we expect that the model is not gonna generalize well because, as I have tried to visualize here, the internal distribution is gonna be different from what we trained initially. Here in this top sub panel, if this is the internal distribution that we've learned, and we want to use that for classification, it might not be an ideal situation because the new representations as presented in the bottom panel might be different. And because of this mismatch, our model is not gonna generalize well. Now, what I want to present as the message is that if we want our models to be stable in situations that something unpredictable has occurred in the input, we need to design mechanisms that can help to keep the internal distribution stable, or at least to change it such that we can incorporate changes in the input. Now, as an example for you to understand what I mean, I believe most of you have not worked with infrared images before, but if you see images like this, more or less you can understand what these images are about, although they are quite different with natural images. Now, if you think why you are able to do it is because you can build relationships between the internal representations of these images in your nervous system and what you expect from what you've learned from natural images previously. Meaning that although colors are quite different in these images, yet in your brain you can identify a geometry of the space and also build relationships with what you know from natural images, and using that you can identify correspondences. And this is what I call autonomous learning, meaning that you haven't presented a lot with infrared images, but you are able to adapt yourself to work well in this new domain, or at least much better than a random starting from scratch or random predictions. However, the same is not true about deep learning, meaning that if you train a deep net for a network that receives its input from natural image domain. If you test that network on the domain of infrared images, it's gonna perform poorly, potentially something in the line of random prediction. And the idea that I want to explore is if we are able to keep the internal distribution is stable, or at least find correspondences between what we are seeing now as something unpredictable with what we learned before, our models can still generalize well. Now, with what I said, I want to move to two applications that we can benefit from this high-level idea. The first one is lifelong domain adaptation. So domain adaptation is a classical problem in machine learning, and the problem is formed as this challenge that we may not observe the same distribution during testing a model. So here in this image, consider that you have a binary classification problem and you've learned this orange boundary between these two classes during training. Now during testing, as in the top oval shape, if we observe the same distribution, then we hope that the model is gonna generalize well. We may have a small number of data points like this green one in the bottom that is not gonna be predicted with the right label, but overall, our model is gonna perform well. Yet, if the distribution has changed a little, in this figure, I've tried to kind of rotate the distribution in this 2D space. The same boundary is not going to perform well. However, if you know that your distribution has rotated and you rotate the boundary, you can see that if I make this boundary somewhat horizontal, then you can use the same model for prediction. Now, the challenge is that in practice, you don't know that your distribution has been rotated. And so if you want to perform well in this new domain where the distribution is a little different, what deep learning, the normal or classic deep learning offers is just collect a new data set and retrain your model from scratch. Now, the goal in domain adaptation is to relax the need for annotating a new data set, which can be challenging given that in many applications we need large data sets, or annotating data might be something expensive, for example, in the domain of medicine. Now, the goal of domain adaptation is to build to use the relationships between these two domains and learn to modify this decision boundary automatically just using unlabeled or unannotated data in the target domain. For example, in this figure, consider that you have a source and a target domain. The idea that we can use is we can use a feature extractor network which is shared between these two domains, although here it seems that we have two feature extractors, but consider that we have the same feature extractor, and at the output of the feature extractor, we learn to align the distributions from these two domains. Or another way to express the same thing using the terminology I used, we use that same, we can learn the same internal or prototypical distribution to represent both domains at the output space of the shared feature extractor. Now, in order to implement this idea, people have used two primary approaches. One of them is to use adversarial learning. Many of you are familiar with generative adversarial learning, where we try to learn how to generate samples or synthetic samples from an input distribution that resemble the real samples. Many of you probably have seen examples of deepfake. It's built upon this idea of adversarial learning, and it's been adapted to be used in domain adaptation as well. The idea is that you train a model on a source domain, and then in order to make it generalizable in the target domain, you amend that initial source classifier, or better to say feature extractor, using a discriminator network, and you play these encoders and the discriminator network against each other, such that the discriminator network cannot identify whether a sample is from the source domain or from the target domain. And this way, indirectly, you are matching the distributions of the source and target domain. Because think about it, if this discriminator network is not able to identify whether the sample is drawn from the source domain or target domain, it means that those two domains are indistinguishable in the embedding space, and that means that if you train a classifier using the labeled samples from the source domain, then that is going to generalize well on the target domain as well. Why? Because the target domain shares the same internal or prototypical distribution in the embedding space. This is probably a more dominant paradigm in unsupervised domain adaptation. The second way to solve this same problem is to align distributions using a probability metric. So the idea is somewhat similar in that we still are trying to align distributions in the embedding space, but the difference is we are not trying to do it indirectly. So if you look into this optimization problem, so the first term is just an empirical risk minimization term. So we are using the samples of source domain to tune this classifier end to end to generalize well on the source domain. And we have this second domain alignment term. So D here denotes a probability distribution. We try to minimize this metric such that the distribution between these two terms are matched in the embedding space. For example, one common distribution that people have used in domain adaptation area is to use optimal transpose and its different variations. And through solving this problem, we can achieve the same goal that adversarial learning could achieve. Now, what is the weakness of current UDA methods, or better to say, something that they haven't explored much rather than categorizing it as a weakness? So existing unsupervised domain adaptation methods need to have access to samples of both target and source domain, because as you can see here, either in adversarial learning or direct distribution matching, we need joint access or simultaneous access to both the source and target domain. And this is somewhat limiting, because it means that we should always have access to source domain. Whereas in reality, when you train a model on a source domain and then test it, And it's not the case that you always store samples from the source domain and you carry that with you all the time. Also, they are, because of this requirement, they are not usable in continual learning settings, which means that we observe the domains in sequence, in a sequence. We are not observing them simultaneously. And this is the motivation of this work, that we try to address domain adaptation in a continual learning setting. So the objective is to model unsupervised domain adaptation in a continual learning setting, which the modeling is not very challenging. We just assume that rather than having the domains at the same time, we are observing just one domain at a time, and then learn that domain and then move to learn the next domain. And then we want to develop an algorithm to address this learning setting, domain adaptation in continual learning. And then to address a new challenge called catastrophic forgetting. Here in the standard domain adaptation, because you are training your model on the source domain during training, it's always gonna be able to generalize well on the source domain. But in a continual learning, that is not guaranteed, because if you update your model to work well on a new domain, your new model might not be generalizable on the past learned domains, because you've updated your model. There's no guarantee that your model is gonna stay stable. In order to model domain adaptation in continual learning setting, as I explained, we assume that we are observing sequential domains. Here, just for simplicity, imagine that we have a binary classification setting. And our goal is to address this learning setting where we don't have samples of source domain or previous domains when we update the model. And the idea that we are going to benefit from is through consolidating the internal distribution, meaning that we are going to assume that in the representation space that we are using for classification, we are going to update the feature extractor such that this internal representation of the input distribution is gonna remain stable. So in order to do this task, we are going to follow these steps. So we are assuming that we are receiving one domain at a time, and then there is an encoder that we use to extract suitable features. Now, during updating the model to address catastrophic forgetting, we are going to benefit from an idea called experience replay. It's a simple idea. The idea is that when you learn a domain, do not throw away all the samples of that domain. Just keep a small number of samples from past domains. How do you identify those samples? That's on its own a good research problem. But what we used was just a simple idea that you can just use samples that are close to the mean of each cluster, meaning that in this representation, in the embedding space, we just store some samples that are close to the mean of each distribution mode. So we replay them back during training on a new domain, and replaying back those samples kind of helps to mitigate catastrophic forgetting. Now, this kind of turns our sequential domain adaptation into a joint domain adaptation problem because of these samples. The upside is that, remember, we are not storing all the samples. We are just storing a small number of samples. And then we were trying to keep this internal distribution stable or consolidated. In order to do that, we model this internal distribution as a Gaussian mixture model. We can do it because if the model is able to predict the right labels through my initial discussion, we are going to have a multimodal distribution in the embedding space. So we can map that distribution with a Gaussian mixture model. Now, storing a Gaussian mixture model is very simple. You just store the means and the covariance matrices. And now, what is the benefit? The benefit is that because we've modeled this distribution, we can always draw samples from this Gaussian mixture model, and we are able to use those samples as a surrogate of the internal distribution that we've learned, meaning that here this Gaussian mixture model is a good approximation for what we learned when training the model on the source domain. And we try to update this encoder network such that this internal distribution remains the same. How can we do it? We can just use that idea of distribution matching. We can match the distribution of the target domain or the current task with the distribution that we initially learned in the embedding space. If we do that, then this distribution here is going to remain stable because we are drawing samples from the Gaussian mixture model, and we enforce the encoder to be updated such that the current task is mapped into the same distribution. As a result, the classifier is going to generalize well on the samples of the current task. And then after doing this process, we select a number of data points from using the same idea of the current task and store those samples in the memory buffer and continue this loop when we move forward to the next task, meaning that in the next task, we have new samples in the memory buffer and we repeat the same procedure. Now, in order to model the internal distribution, as I mentioned, we are using a Gaussian mixture model. Learning a Gaussian mixture model in its broadest case is not as easy. People use methods like EM algorithm primarily. However, here our problem is much simpler. The reason is, first of all, we know how many modes we want to use. That's equal to the number of classes that we have. On top of that, we know the labels for each mode. So rather than training a Gaussian mixture model, we can break that into, if we have K classes, we can break this problem into learning K independent Gaussian distributions. And in that, that's a simple problem, right? Just in a simple statistics course, we learn how to estimate the mean and covariance matrix for a Gaussian distribution given some samples. And then this is the optimization problem that we solve during model updating. What we do is, these are samples that we have in the memory buffer. We use them to keep the classifier generalizable on samples that we have in the memory buffer. In addition, we use the samples that we draw from the internal distribution as well, just to make sure that the classifier always generalizes well on samples that are drawn from the internal distribution. And we match, using these two terms, we match the internal representation of the memory buffer with the internal distribution that we have estimated, and also samples that we have from the target domain. Now, I've used these two terms because kind of they give me better results compared to using just a single term matching the just one of the distributions with the internal distribution. And similar to many works in deep learning, you come up with this exact form of optimization through trying several alternatives and choose the one that gives you the best result. We performed experiments on, I think, four domain adaptation problems. So I think three of them, we have 3 domains, and the fourth one, we have 4 domains. And then the model is a backbone model, which is models our encoder, and followed by some fully connected layers as our classifier according to the decomposition that we had before. We use classification accuracy for evaluation. We generate learning curves, which I will explain, and we compare against some of existing state-of-the-art UDA algorithms. So here I've included learning curves for these 4 data sets. So each column corresponds to one of the domains or one of the data sets, and each curve corresponds to one of the domains. So consider this subplot A here. Here we have this task, learning from SVHN, then moving to MNIST, and then moving to USPS. These are 3-digit recognition tasks. And here we've plotted the learning curves and we've generated the learning curve by reporting performance on the testing split of data versus training epochs to model a notion of time, meaning that we are learning in time and we are continuing to update the model and check its performance on the testing splits. And every 100 epoch, we move to a new domain. So here you can see when we move to a new domain, for example, here at 100th epoch from SVHN to MNIST, first of all, performance on MNIST is much better than random performance, which is 10%. It is 60%. That's because we are not learning from scratch. The internal distribution is informative, and then through internal distribution matching, we are able to boost performance from 60% to something around 90%. And our performance on the initial domain, which was SVHN, is going to decrease. That's because the samples that we stored in the memory buffer here are, if I remember correctly, less than 1% of it was. I think it was 100 samples in total, so 10 samples per class. So because we are approximating the whole SVHN data set with just 100 samples, we are going to observe some forgetting effects, but still you are seeing that our performance decrease is just maybe at most 5 or 6%. And the model is able to move to a third domain and learn a new domain, continue to perform well on the previous domains. And remember, the new domains are learned without using a label in that new domain. And this is something, from what I know, somewhat unexplored. Now, we also did some comparison against current domain adaptation algorithms. And what was interesting is that in one of the data sets and most of the tasks in another data set, we are able to perform as good as some of the best learning algorithms, as you can see in this figure. And the reason is, although we didn't use the samples from source domain for domain adaptation, but this keeping the internal distribution stable and consolidated turns out to be as good as using the direct samples. And this way, kind of for a normal domain adaptation problem, our algorithm reduces to domain adaptation without using source domain data. That's on its own a learning framework called source-free domain adaptation, and that's also a subset of what we did before. Okay, I think I'm done with domain adaptation. At this point, I want to move to the work on presentation attacks. Seems there's no question, so I guess I'm going to move forward. Okay, so we are going to use a similar idea in the area of presentation attack detection. What are presentation attacks? This is a topic that is explored by a biometric community. You probably have used your fingerprint or your face in a more recent smartphone models to gain access to your phone. This is something that is used extensively in areas that we want to limit access to information through some identifier from humans, mostly fingerprints and face images. Now, we also have adversaries that try to gain access to systems that they are not allowed to visit or explore. And so what adversaries do, they try to generate samples of fingerprints or face images such that they gain access. In the area of face presentation attacks, the simplest method is just maybe to print face image of somebody who you know that has access to that system, and use this printed image to gain access. Now, in order to improve security, we want to design algorithms that can detect samples of attacks and do not authorize access for those samples. The way that this problem is solved in the biometrics community is that you build a data set. It's somewhat similar to a binary classification problem. You build a data set in which you have samples of bona fide images of real humans, and then presentation attacks, samples, building upon my example, samples of printed images, and you train a classifier that is able to distinguish between bona fide samples and presentation attacks. And then during testing, you use this to identify presentation attacks. Now, the challenge that we have is that current methods for presentation attack detection are trained in a one-shot training testing framework, meaning that here we train the system, and then training is finished. We don't do training anymore, and then we just fill the system and use it forever. I mean, not maybe forever, but at extended time periods. Now, the challenge for existing methods is they are vulnerable with respect to novel presentation attack types. So here, building upon my example, I said that here in your training data set, you can include samples of printed images and the real images or bona fide samples. Now, the adversary might be more clever and design a new type of presentation attack. For example, you can use masks that are more similar to human face compared to just a printed image. And if you have that sample, that new type of presentation attack, your system is going to be vulnerable with respect to, and these presentation attack types are generated. Now, our motivation is to address this challenge for PAD systems. So the objective is to model presentation attack detection in a continual learning setting, meaning that we are going to continue training during model execution as well, building or similar to previous example. We are going to relax this one-shot training testing procedure. And something that is a little different from the case of domain adaptation, we are going to enable a PAD system to identify novel attack types. And then by collecting novel attack types, we want to enable the system to autonomously update itself and to learn those presentation attack types so that in the future, the system can identify them automatically. So this, we have to address two tasks. One of them we call anomaly detection. We need to detect samples that are novel. We haven't seen the similar samples before. And then we want to address continual learning challenge as well, meaning to update the model as we see the data stream. We want to identify novel PAs and then use those novel PAs to update the presentation attack detection system. And then this system is going to be able to identify the novel PAs in the future as seen PAs. Now, in order to address these two goals, so the framework that we are going to pursue is that initially we are going to assume that we have a data set of presentation, some known presentation attacks and bona fide samples, and train a system. This is something that is similar to existing methods. And during model execution, we want to identify novel attacks at samples that are outside the learned distribution in the embedding space or the prototypical distribution. So this is a prerequisite for our method. We are going to be able to identify only presentation attacks that are different from what we've seen before. So if the adversary is able to just alter some of the presentation attacks in a minor way, we might not be able to identify them. But if we are seeing novel attack types that are significantly different, we are going to be able to identify them. And then we are going to collect these novel samples, and on some intervals in time, which is a design choice, we are going to update the model using these samples and samples that we store in a memory buffer. So it's a similar idea that we used before for domain adaptation, to update the model such that model is able to identify the new presentation attacks as known attacks, and at the same time maintains its ability to identify the past learned attack types. So now, what is the challenge for anomaly detection? So when we think about anomaly, the word suggests that the sample is quite different from the training data set. The challenge in deep learning is that deep nets are very overconfident about their predictions. For example, I did a simple experiment. If you train just a 2-layer MLP network, the simplest network, for binary classifications of digits 0 versus digits 1 from the MNIST dataset, then its confidence on the if you feed a sample from 0 or 1 is 99.9. So it's very, and you can also imagine that this is a simple problem, binary classifications of zeros versus ones. So this is good if you are interested in just this binary classification problem. However, if you train, if you test this network on the digits from 2 to 9, again with a confidence of 94.8%, your network is gonna identify them as zeros and ones. So in a just using the a neural network, it's not gonna be easy to identify anomalies because the network is very overconfident about its prediction. And also it suggests that if that's the case, I know this is a simple problem, but if you have maybe in practice, the situation is not as severe, but it suggests that PAD systems can be very vulnerable with respect to new attack types, because the system is gonna associate an input with some label with a high probability. Now, in order to address this challenge of anomaly detection, we are going again rely on this idea of checking what happens with respect to the internal distribution. So presentation attack detection inherently is a binary classification problem because you are just interested in determining whether this input is bona fide or presentation attack. So from previous discussion, we know that the DeepNet is gonna learn this as a GMM with just 2 components. And then the classifier is probably going to learn a decision boundary between these 2 clusters of the internal distribution. Now, the idea that we are going to explore is that if the encoder observes a sample that is similar to the training data, it's gonna lie close to the cluster of the either bona fide samples or presentation attacks. So the vulnerability of DeepNet stems from these areas that the network is very overconfident. So if the adversary can design presentation attacks that lie away from this decision boundary at the side of the bona fide samples, yet very different from bona fide samples, the system is going to identify them as bona fide samples. So our goal is to identify samples that lie outside this learned distribution as samples that are novel. So the samples that are quite different from the internally learned distribution, we are going to identify them as the novel presentation attacks. In order to do that, so as I said, we have a binary classification problem. What we can do here, we can just add a third class for novel samples, and those novel samples are samples that are significantly different from the internal distribution that we've learned. So obviously, this is again a design parameter. What do you mean by significantly different? So in what I used, I assume that samples that lie two times away from the mean of each cluster as novel samples, samples that are quite different from what we've observed during training. And during testing, when the model is being tested on a time-dependent stream of data, if some data points lie in the novel portion of the internal representations, we are going to flag them to be as novel, and then at some time periods, we are going to update the model using these identified novel samples so that the internal distribution changes such that in the future we know that those are presentation attacks. And so in order to address continual learning, again, it is similar to the case of domain adaptation. We can just store samples that are close to the mean of the bona fide samples and presentation attacks. And when we update the model, we replay these samples that are stored in our memory buffer because our goal is our model maintains its generalizability on previously seen samples. And so the optimization problem is somewhat similar in the case of domain adaptation. Just we match the distributions, we keep the internal distribution stable. And for experiments, we've tested on two data sets. One of them has 11 different types of presentation attacks, and the other one has 9 type of presentation attack. And we perform experiments in single PA and binary PA emergence setting. Single PA, we mean that at each time.
Just want to give you a 5-minute warning.
Yeah, I think I'm done. But I guess we might be short on questions. And then I was saying, talking about the single PA and binary PA emergence setting. In single PA, we imagine that novel attacks are emerging one at a time, and in binary case, they are emerging 2 at a time. And we generated learning curves similar to the case of domain adaptation, and we compared against the static or single training, which is state-of-the-art or existing methods, and then joint training, which means just having a retraining model from scratch. This is ST is our lower bound, joint training is our upper bound, and 3 methods of sampling. So here you can see the results. We have learning curves. In each one, the upper bound is this dashed blue, green one, and the lower bound is the dotted blue ones. And you can see that our method is able to improve upon the single training, and as it observes new presentation attacks, it is able to first identify the novel attacks and then build upon them. So I guess sorry for taking too much. I guess I should have planned to make it a little more condensed, but hopefully I can answer to a few questions. If you have any questions, do email me in this email. You can also check the papers. I should have probably put link to the papers as well, but if you email me, I can share the papers as well. Thank you.
Thank you. Any questions? I have a quick one. Have you ever tried to use images? So they're the same, what you call different domains, but one is basically an image as you would think about it. The other would be like numbers underneath it. And the reason I'm asking is in meteorology, one of the things that we do a lot is looking at cyclones, for example. So you could have the satellite image of the clouds, but you could also have the pressure information. And we don't have that many satellite images, but we have a lot of pressure information. So the idea is we'll be able to recognize cyclones, atmospheric rivers, like things that matters in terms of like disaster relief.
So I haven't done that in this work, but yes, so kind of, I believe you are talking about multimodal domain adaptation. Here we assume that both modalities are the same. We had images, but yeah, there are works on multimodal. The ones that I'm aware of, I'm not in your area, obviously, but there are works on domain adaptation using speech and image modalities. That's particularly helpful for videos for which you have images and speech at the same time. Now the goal would be, as you explained, sometimes you may want to kind of from speech infer some information about vision, or maybe vice versa. Yeah, there are works, but in this in the works that I covered here, I haven't done experiments on a multimodal domain adaptation.
Thank you. Well, let's thank Mohammad for a great talk, and I think you know where to find him. And we'll talk to you next week for our next seminar. Thank you.
Thank you.